At 7:42 in the morning, a driver reaches an intersection and stares at a red light. The cross street looks almost empty. The urge is obvious. Why is the city making everyone wait? But that red light may not be a mistake. It may be a deliberate sacrifice, holding one line of cars for a few more seconds to stop a much larger jam from forming 3 blocks away. In traffic management, the fastest move is sometimes to slow someone down. Hiddenova follows the morning rush from that single red light into the machinery that decides how a city moves. A traffic jam rarely begins as one dramatic failure. It starts as a small imbalance. A turn lane fills, a bus blocks a lane, a signal changes too soon or too late. Then the delay spreads backward through the road network. To fight it, cities use sensors, time signals, control rooms, navigation data, and planning models. Each part sees only a fragment. Together, they try to answer one question before drivers feel the answer in their brakes. Where will the next blockage begin? The prediction begins where the driver barely looks, at the roadway itself. Traffic sensors are the city's first witnesses. Depending on the street and the equipment installed, a sensor may detect that a vehicle is waiting, estimate how many vehicles have passed, or recognize that a queue is growing. The purpose is not to identify individual drivers. It is to measure motion, presence, volume, direction, and sometimes speed. This matters because a traffic jam is not just a lot of cars. It is a change in flow. A road can be busy and still work, as long as vehicles keep moving in a stable rhythm. The warning sign is when arrivals exceed departures. Cars enter a lane faster than the intersection can release them, and the queue begins to stretch. A sensor cannot solve that problem by itself, but it can send the first signal that the balance is shifting. From there, the city must decide whether this is a normal surge or the start of a breakdown. Once the street reports that pressure is building, the next question is timing. A traffic signal is not simply red, yellow, and green. It is a negotiation between competing movements. Cars going straight, vehicles turning, buses approaching stops, pedestrians crossing, and cyclists entering the junction. Giving more green time to one direction takes time away from another. That is the central tension of signal control. A city may extend a green phase to clear a queue, but if it holds that green too long, traffic waiting on the side street may spill backward and block another intersection. The system is trying to prevent one local fix from becoming a wider failure. This is why a light can feel unfair from inside one car. The signal may be protecting a route the driver cannot see. It may be keeping a corridor open, preventing a left turn lane from overflowing, or stopping traffic from blocking the box. The red light is not only a stop, it is a choice about where delay will be placed. Individual intersections are only the visible pieces. In a traffic control center, operators and systems watch the network as a whole. Screens may show camera feeds, maps, signal status, reported incidents, and changing congestion patterns. The key shift is scale. A driver sees one light. A control room sees how that light affects the next one, and the one after that. If traffic backs up onto an upstream road, a delay becomes a blockage. If a blockage reaches a major junction, the city can lose capacity in several directions at once. Control centers exist because congestion is contagious. A disabled vehicle, a construction lane, a sudden crowd leaving an event, or heavy demand after work can send pressure through connected streets. Operators can adjust signal timing plans, monitor whether changes are helping, and coordinate responses when a normal pattern no longer fits. But every adjustment has a cost. Clearing one corridor may force another to wait. The task is not to make traffic disappear. It is to keep the network from tipping into gridlock. Roadside equipment is not the only source of information. Navigation data adds another layer, because drivers themselves carry signals through their phones and vehicle systems. In broad, aggregated form, this kind of data can reveal travel times, route choices, and changing speeds across many streets. That creates a powerful feedback loop. If a main road slows, navigation tools may suggest alternate routes. Those suggestions can relieve pressure, but they can also move traffic onto streets that were not designed for heavy demand. The city then faces a new problem. Congestion is no longer only where the original bottleneck formed. It can be redistributed by digital advice. This is one of the sharpest paradoxes of smart traffic management. Better information can help individual drivers escape delay, while also changing the shape of delay for everyone else. A control center may see a corridor improve, Then watch a residential or secondary route begin to strain. Prediction is no longer just about vehicles already on a road. It is about where drivers may choose to go next. Prediction requires more than looking at the present. Cities also use planning and modeling tools to test what might happen under different conditions. A model is a simplified version of the road network, built to explore cause and effect. What happens if a lane closes? What happens if signal timing changes along a corridor? What happens when a new development adds more trips to nearby intersections? These tools are not crystal balls. They depend on assumptions, data quality, and the limits of the model, but they allow planners to see consequences before concrete is poured, or timing plans are deployed. This is where traffic management moves from reaction to prevention. If a model suggests that a turning movement will overwhelm an intersection, the city can consider changes before commuters are trapped in the result. If a corridor is sensitive to small disruptions, managers can prepare alternate timing plans. The future jam is treated like a design problem, not just a morning complaint. Even with sensors, signals, control rooms, navigation data, and planning tools, traffic remains difficult because every driver is part of the system being managed. People brake suddenly, change lanes, hesitate at turns, avoid tolls, follow apps, ignore apps, or choose a route based on habit. Weather, deliveries, emergency vehicles, roadwork, and events can change demand faster than a plan expects. The road network also has physical limits. A narrow bridge, a short turn lane, or an intersection with many competing movements cannot process unlimited traffic just because software is watching. This is the important restraint at the center of the story. Traffic technology does not create infinite road capacity. It allocates scarce space and time. The best outcome may not be a free-flowing commute for everyone. It may be a managed slowdown that prevents a worse collapse. That is why the morning red light can still feel frustrating even when the system is working. It is solving a problem larger than the driver's view. The city's traffic system is not a single machine with a master switch. It is a chain of measurements, predictions, and compromises. A sensor notices pressure. A signal redistributes delay. A control center watches the pattern spread. Navigation data changes where drivers go. Planning tools test which decisions may hold under stress. The result is not perfect movement, but managed instability. The final implication is uncomfortable. Preventing a traffic jam often means creating small delays on purpose. The red light that annoys one driver may be the barrier keeping a larger failure from reaching the next intersection. If you have ever wondered why a light held you at the worst possible moment, comment with your theory. Like this video and subscribe for more cinematic breakdowns of city systems.